Let's continue our study of vertical circles, still at the physics amusement park. And let's say after the Ferris wheel, you're like, yeah, that was nice, but maybe I want to challenge myself and do a little bit more of a thrill ride. Let's try the Looping Starship. I don't know if you're familiar with the Looping Starship. Maybe you're familiar with more like the Buccaneer, sort of that ride that goes back and forth and back and forth. And this is a very similar one. It goes back and forth and back and forth, but eventually it goes all the way around. So it loops all the way around when it gets fast enough. So let's do a very similar thing to what we've done before. Now, of course, as it goes up, it slows down and speeds up and slows down and speeds up and slows down. So is this uniform circular motion? No, this is actually non-uniform circular motion because the speed is changing. That doesn't really mean anything changes about the way we approach the problem, specifically if we look at the top and the bottom. So let's identify those two locations, and we'll do a very similar idea. In fact, let's start at the bottom. So let's go ahead and draw a picture, a real simplified picture of what the vehicle looks like, something like this. If you want to get more detailed, of course, you can. I'll draw a person in there again, having the time of their life, woo! Having a great time there. And we are focusing on the person. We're going to be drawing a free body diagram of the person. So just go ahead and pause the video. We're going to draw velocity, acceleration, net force, and the free body diagram for our person here at the bottom. And so let's say our person's going to the right, because that's the forwards direction for the vehicle. I mean, they're accelerating upwards, and net force is upwards, because of course the center of the circle is above them. And we're going to draw our weight straight down, and since the net force is pointing up, of course, normal force is going to beat the weight. And so hopefully you see this is literally the exact same thing that we had at the bottom of the Ferris wheel. Maybe we're going faster, but it doesn't matter. Nothing really changes about our free body diagram or our vectors off to the side. And so let's work smarter, not harder, right? If it's the exact same free body diagram, let's not go through the whole derivation of the equation because we know what's going to happen. It's going to be the same thing. If you want to practice, you certainly could write sigma f equals ma and build it all up and solve for n, but it's going to be the same thing. So you know what? Let's just get the exact same result that we had before, just write it down, right? The normal force is going to be larger than the weight by this factor of mv squared over r, and here I pulled m to the outside, but again, if you didn't want to do that, you can write n equals mg plus mv squared over r, whatever makes more sense to you. But again, there's no reason to go through the whole thing because it literally looks the same as before. Okay, so now let's fast forward and go to the top. So now we're going to draw the whole picture upside down, because you're upside down at the top, right? It loops upside down. And pause the video. I want you to do the same thing. Draw velocity, acceleration, net force. Draw your free body diagram. Okay, so a couple details. One, of course, is that now you're moving to the left because, of course, we're going in that circle, right? And so the velocity is to the left. And notice I also drew the velocity vector smaller. Right? Let's be detail-oriented. This is non-uniform circular motion, right? We're going slower at the top. So let's draw the velocity smaller. That makes sense, right? This centripetal acceleration and net force, of course, have to point to the center of the circle, which is now below the person. And so, of course, they're going to point down. We're going to call down the positive, just like before. And, of course, we're going to start with weights on the free body diagram, pointing which way? Of course, straight down, right? Now, what else do we have here? Well, there's going to be a normal force because the person is, pressing against the seat. And which way is that normal force going to point? Well, it's not up, is it, right? Because if it were have the normal force pointing up, we'd have the exact same situation as the Ferris wheel. And why would we do the exact same situation? I mean, I know at the bottom is the same situation as the Ferris wheel, but why would I do a whole other series of situations here that is the exact same thing as we did before? That's kind of a waste of our time because the normal force isn't the same. Let's think about this, right? Normal force comes from the surface, and the surface is the seat. And where is the seat? From our perspective, where is the seat relative to the person? It's up here. And so what's the only way our person could be pushing on the seat? From our perspective, our person is pushing up against the seat, right? That's the only way, because it's not like the person's going to pull down the seat. It doesn't make any sense. And so by Newton's third law, if our person pushes up against the seat has to push down. Yeah, that's right. The normal force actually should be pushing down on the person. That's the only thing that makes sense based on where the surface is. And so the normal force does push down. Now, how long is the normal force compared to the weight? Well, here I arbitrarily drew it shorter, but it could be longer. It really depends on the numbers involved. We have no information about that, so it's totally a guessing game. So just draw normal force pointing down, and maybe it's even equal to the weight. In fact, there's no information that would tell us one way or the other, so it doesn't really matter. As long as we have the normal force pointing straight down, that's the idea. Okay, so now go ahead, pause the video. You're going to build up your sigma f equals ma equation. You're going to solve for normal force. Let's see what you get. So I'm going to do it in full here because this is definitely a different situation. And we have sigma f equals mac, just like usual. And down is positive, and mg and n are both pointing down. So they're both positive, right? It's going to be mg plus n equals mv squared over r. This is a distinctly different situation than we've seen before. And now again, we solve for normal force, so just subtract mg over to the other side, but nothing fancy here. And then if you want to get fancy, you can pull a mass to the outside, make it look kind of sophisticated. Totally up to you how you want to express it. Okay, so again, at the bottom, totally the same as the Ferris wheel. At the top, definitely different because our person is upside down and the normal force has changed direction to pointing down instead of supporting the person from below.